Hello, thanks for joining us. On behalf of the Environmental Finance Center Network, welcome to our webinar, Get to Know Emerging Drinking Water Contaminants, PFAS Challenges and Solutions. My name is Tess Clark. I work here at the Syracuse University Environmental Finance Center. And as you may know, this is the second webinar we're hosting on per and polyfluoroalkyl substances, or PFAS. I know many of you attended last week's introductory webinar, so welcome back. If you are just joining us, you can always go back and watch last week's webinar on the EFCN website. Here are some logistics to keep in mind. During today's session, everyone will be on mute to ensure audio quality. If you have a question, just type it into the GoToWebinar question dialog box anytime throughout the session. All of the questions will be reserved for a Q&A at the end, but feel free to send questions at any point. Like I mentioned before, this is the part 2 to our first webinar on PFAS. And if you attended that webinar and had more questions related to the treatment solutions, we will be covering that information today. We will also be making today's slides available as well as a video recording on the EFCN website. You can reach that website at www.efcnetwork.org. And if you missed the first webinar, you can watch that there as well. As a courtesy, we like to provide a certificate of attendance for participating in our webinars. We do not submit our webinars to licensing agencies for pre-approval of continuing education credits, and you must attend the entire 60-minute session to receive one. If you watch the webinar with a friend or you're not directly logged into our webinar or you're not registered, we will not have a record of your attendance. Again, we can't guarantee that our webinars will meet the criteria for continuing education for any given agency. Certificates will be sent via email within the next 30 days. And now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small public water systems in all U.S. states and territories to help local water systems achieve their goals and stay in compliance with the Safe Drinking Water Act. And our center, Syracuse University EFC, is based, of course, at Syracuse University in Central New York. We focus on assisting small and rural communities in EPA Region 2, especially in areas related to environmental infrastructure and community resiliency. We hope that these webinars can be a resource for you, whether you've been impacted by emerging contaminants, new regulations, or just need to learn more. And on that note, I'd like to introduce Kyle Hay. Kyle is joining us from Weston and Sampson, one of the leading design and engineering firms in the US. As a project engineer in Weston and Sampson's water group, Kyle has worked on multiple PFAS-related projects in New England, including work at the former Pease Air Force Base and the former Devens Army Base. So welcome, Kyle. Thanks for sharing your information with us, and take it away.
All right, thank you, Tess.
Thanks.
So this is a continuation of a two-part webinar series. Last week, Steve LaRosa talked about PFAS background and some of the sampling procedures and where we're at with regulations. And today I'm going to talk about challenges with regards to treatment and a few case studies. So here's a quick presentation overview. So for those of you who did not attend or would like to get a quick recap on the background of PFAS, I'm going to spend a few minutes on that. I'm going to talk about some of the existing treatment technologies that are on the market and commonly used for PFAS treatment before diving into some of the more emerging treatment technologies that are starting to be developed. After that, we'll dive into two case studies, one at the former Pease Air Force Base in Portsmouth, New Hampshire, and another case study at the former Fort Devens Army Base in Devens, Mass. After that, I'll have some time to follow up with any questions that the audience may have. So for those of you unfamiliar, PFAS stands for per and polyfluoroalkyl substances. It's a fluoropolymer compound that's characterized by a carbon-fluorine bond. And this bond, this C to F bond, is one of the strongest known bonds in existence at this time. And so PFAS are man-made compounds that utilize this bond for a whole host of different purposes. So as shown on the slide there, PFAS are resistant to many different things, including oil and grease, resistant to staining, it's water resistant, it's heat resistant, and because there's so many useful properties to PFAS, there's over 3,000 known compounds in this perfluoral, polyfluoroalkyl class of chemicals. So recently, though, PFAS has been in the news more and more, and that's primarily because of the evolving health studies related to PFAS and the bioaccumulative properties and lack of degradation properties of PFAS. So PFAS, once it gets into the environment, it does not break down. Oxidizing and biological activity do not break the carbon-fluorine bond, and so they're very resistant to environmental oxidation. And they're also bioaccumulative within a human body. So this bioaccumulative property can last anywhere from 1 week within a human body to over 10 years. And that is primarily based off of the chain length. So looking on the right-hand side of the screen, you see PFOA and PFAS, two of the most commonly referenced perfluoral compounds. And so these are both considered long-chain compounds. They have 7 and 8 carbon atoms in the backbone of the compound. And so these are long-chain compounds. They are have more known health impacts than what's referred to as short-chain compounds. And short-chain compounds are perfluoral compounds with less than 6 carbon atoms in the sulfonic acid group, or less than 7 carbon atoms in the carboxyl acid group. So sulfonic groups are the ones that end in S, and carboxyl groups are the ones that end in A. So based off this chain length, we will see different health impacts, but we also see different treatment impacts. So looking at what PFAS are used in sort of everyday products, it's a whole host of modern worldly technologies. Waterproof boots, waterproof fabric, as you can see in the Denver airport there, are coated in PFAS. Grease resistant, as seen in the pizza box, fast food wrappers, microwavable popcorn, anything that is designed to repel or resist grease staining is often coated with PFAS. Carpeting or new furniture has PFAS coating on it to repel staining. And there's also that nice property of PFAS in that it can withstand very high temperatures. So oftentimes it's used as a flame retardant. So in child's pajamas, there's often a PFAS coating on there. And then early on, and still used, is what's called AFFF, or aqueous film forming foam, which is a firefighting foam designed to put out high temperature hydrocarbon fires. And so all of these different products can result in environmental releases. So historically, and this would really be up until around 2018, we really looked at where PFAS got into the environment in high concentrations. And so typically that was airports, military installations, firefighting training academies. And so those 3 or 4 different places were primarily due to AFFF release. So oftentimes airports or military installations that had runways would stockpile or train with the firefighting foam in the event that there was an airplane crash, and they would use the foam to put out the fire or practice putting out fires. That foam gets into the groundwater and then can cause a pretty large-scale plume. So kind of the last one on this slide, though, is manufacturing facilities. And so manufacturing facilities can release PFAS if they are either producing any sort of PFAS compound, or if they are using PFAS as a step in their manufacturing process. So if you have a facility that is waterproofing fabric, but they're using PFAS, that can still result in a release of PFAS. But more recently, kind of since 2018, we started to see more and more locations with positive PFAS in the soil or in the water. And so recently, as analytical sampling methods have improved and we see detection levels going down and being more accurate, we see PFAS in all sorts of a host of places, like car washes, agricultural land where biosolids are spread, and biosolids coming from wastewater plants, so there's often PFAS in wastewater. Private septic systems can have PFAS. Anything that's excreted from a human body or washed off your Teflon pans and goes down the drain often ends up in a septic field. Landfills, and that's either from accepting sludge from wastewater plants or accepting those modern products that I was discussing. Waterproof fabric, old carpeting or furniture often has PFAS, which can seep out of the products and get into the landfill leachate. And then more and more, we're starting to look at PFAS in food. So not necessarily just in plastic packaging of food, but also just in fruits and vegetables that you might grow in your own backyard garden. Anywhere that you are working sort of in the modern world, there's a good chance that there's PFAS in it. And whether that's plant uptake from vegetables or animal uptake from feed, we kind of are starting to see PFAS in a whole host of places. So this is a real nice infographic kind of made by the state of Michigan to talk about the PFAS cycle. And so as we are starting to see lower detection levels in the laboratories for PFAS, we can start to look at the PFAS cycle in a more holistic manner. So on this graphic, we can see that there's a whole bunch of different arrows and transport routes that PFAS is moving through the environment. So on the manufacturing side, you can have discharge to surface water sources or to wastewater plants. Once the wastewater plant gets it, it can either be discharged into your surface water supply, or it can be transported as sludge to a landfill or biosolids to an agricultural land. Leachate from landfills can go back to the wastewater plant, and you kind of have a cycle right there where wastewater plants are sending activated sludge to the landfills that has PFAS in it, and then it gets into the leachate and comes back to the wastewater plant. We see release again from firefighting foams, which can run off into surface water, or it can seep into the groundwater supply. And then we also see a lot of spreading of PFAS just through spreading of water. And so whether that's through drinking water to residential use, or irrigation water, possibly pulled from a local river or aquifer to irrigate farmland, can also spread PFAS in that manner. So as we see those detection levels go down and we see the public awareness go up, we see the amount of sampling and the positive hits from that sampling increase as well. So here's a nice map put together by the Environmental Working Group, trying to track all of the known positive PFAS samples in the environment across the country. And so a lot of these hotspots may be from military or manufacturing installations. We're also starting to see more and more from other reasons I had mentioned earlier. And you do see in some states that there's high amounts of positive samples, such as Michigan, for example. And there's a good chance that Michigan does not have higher than average PFAS in their environment. There's a good chance that they are just being more proactive and sampling more locations, which results in more positive detections. So before we go on to the treatment side, I just wanted to kind of reiterate the structure of PFAS. And so that carbon-fluorine bond, which forms the backbone, has an absorptive property to it. So it can bond well to organics. And so that adsorptive property is based on the chain length. So the more carbon-fluorine bonds in that backbone, the more adsorptive the PFAS compound will be. Conversely, the head group, which is the compound on the functional group on the end of the compound, is anionic, so it has a negative charge. So that negative charge can be useful when we talk about different filtration media such as ion exchange, as it gives us something to kind of bind onto. On the right-hand side, we also can look at the surfactant properties of PFAS. The head group of PFAS, for example, is hydrophilic, so it likes water, where the backbone is hydrophobic, so it repels water. So with this surfactant property, we can try to use that to our advantage in terms of treating or concentrating PFAS solutions. So when we look at drinking water treatment technologies that are on the market at the moment, the most tried and tested option is using granular activated carbon, or GAC. So GAC is largely a commodity at this point in drinking water systems. Because there's so much of it available and on the market, it's a cost-effective strategy for removing PFAS from your water supply. And there's also quite a few installations for PFAS treatment already installed and in use in the United States. So from that, we can get a whole host of data based on how long we think the PFAS will stay absorbed to the carbon, essentially how long the GAC media will last. And we can also look at that existing data for things like head loss or operational costs. So there's a good host of background information and data that we can use when evaluating treatment options moving forward based off GAC. So another advantage of GAC is that because it relies on absorption, the PFAS compound will adsorb to the media, and then whenever the GAC filter is spent, or essentially the available adsorption sites are taken up, we can transport that GAC media off-site to a reactivation facility or an incinerator and heat the carbon up to a temperature where the PFAS breaks apart. Essentially, once you get to around 1200 degrees Celsius, that carbon-fluorine bond will break apart and you can thermally destroy the PFAS. And so that's nice for a lot of systems in that they don't have to worry about on-site destruction of PFAS. Once they absorb to the filter media, they can ship it off to a reactivation facility and it's out of their hands. Disadvantages, though, associated with GAC is that if you are trying to treat essentially all compounds or primarily short chain compounds in your water, so those are the compounds that have 4, 5, or 6 carbon-fluorine bonds in that backbone, they may not adsorb as well to the media as the long chain ones, such as PFOS and PFOA. So because they don't absorb quite as well, you will have shorter run times, shorter bed lives, and you might be preemptively changing out your GAC media to try to hit those targets that you have, which can get quite expensive quite fast based off your concentrations and your flow rates through the filters. Another disadvantage with GAC is that they require a large amount of contact time. So the industry standard at this point in time is 10 minutes of contact time in a filter to remove your PFAS. Because of that, we see large filters being required for moderate-sized flow rates or contaminated wells. So this can result in large building footprints and large building heights because you need a certain amount of clearance over the vessel to be able to maintain your filters. When we look at a newer developing technology that's starting to really get a lot of focus in the market, it's ion exchange resins. So ion exchange resins are essentially plastic beads that have a coating or a surface that promotes not only adsorption of PFAS compounds, but also ion exchange properties. So you will adsorb the backbone structure of the PFAS compound, but you will also release chloride into your water in exchange for taking up the head group of the negatively charged PFAS. So because we have this dual method of treatment, adsorption and ion exchange associated with resin, we see that we're seeing more efficient run times and lower contact times required to see equivalent PFAS removal. So with this kind of custom designed treatment associated with ion exchange resins, we can see this longer life. The lower contact time results in smaller vessels, which can result in smaller building footprint, smaller land footprint, and oftentimes they're shorter vessels as well, which means you don't need to go quite as high if you're putting these vessels inside of a building. Disadvantages, though, for ion exchange resin is that it can be quite expensive compared to GAC because there is limited volumes on the market and also limited manufacturers on the market at this point in time. Being a newer technology, there's less data available. It's really only been within the last 2 or so years where we started to see resin really pick up and be a viable option for PFAS treatment. And so because of that, we don't have the best handle on either run times or O&M costs associated with running the resin for PFAS. And so oftentimes longer run pilots are required to make sure that the engineer or the designer has a good grasp on how the resin will react for that specific water supply. And so really the last viable option for treating drinking water or large volumes of PFAS contaminated water is either nanofiltration or RO membranes. And so whenever you have a contamination of a water supply, usually these low molecular weight membranes are always an option. You see very good removal efficiencies for both long chain and short chain compounds, oftentimes over 99%. But there is a host of disadvantages associated with membranes beyond just the high capital and O&M costs associated with operating a membrane facility. And primarily the main disadvantage is trying to figure out what to do with the waste stream. So the waste brine that is backwash off the membrane still has high levels of PFAS in it, and the operator or the designer will have to figure out what to do with that PFAS. Oftentimes with membrane filtration systems, there will be an extra GAC filter or resin filter that is just used to handle the waste stream. So when you have just a low volume of waste, oftentimes you can have just a single GAC vessel off to the side, and you can run empty bed contact times in the hours up into the days, and basically use it as a super loader to try to absorb as much PFAS onto the media as possible. And then that spent GAC media will then be transported offsite for reactivation. So when we think about other common treatment technologies for drinking water, there's a whole host of other options that are out there, but none that have been proven to be successful for removing PFAS from water. So that includes things like aeration, coagulation, floccumentation, sedimentation does not remove PFAS. Conventional rapid filtration with either sand or anthracite does not remove PFAS. And conventional oxidation is not shown to have large success removing PFAS. And so that includes things like disinfection with chlorine or oxidation with UV or ozone. So none of these commonly used treatment technologies that you may have in place at your drinking water treatment plant are effective for removing PFAS. So looking at some of the more emerging technologies for PFAS, things that are being developed in labs around the country and around the world, we really can kind of separate them into two categories. And so that first category is trying to figure out a way to destroy PFAS primarily on site, so that it doesn't require transport off-site to an incinerator or a reactivation facility. And so these two technologies that are showing promise is electrochemical oxidation and plasma treatment. And so both of these treatments use high voltages and high currents of electricity to basically form free radicals that can break that carbon-to-carbon bond. So these technologies have been proven to reduce the chain length of PFAS. So essentially turning an 8-chain PFAS into a 6 or 4-chain PFBS. And so these short chain compounds have less dangerous health impacts from the current toxicology results. And so there's some promise there that if we can reduce the amount of more toxic PFAS into less toxic PFBS, that might be successful. There's also some promising results that show that at certain voltages and certain amounts of contact time within these reaction cells, that you might be able to actually break apart that carbon-fluorine bond, which would essentially remove the resistant man-made bond that's been manufactured. So the downside, though, with these two treatment technologies at this point in time is that they require several hours to be able to see the oxidation of PFAS required to successfully say that the PFAS is limited to a safe level. And so because it requires so much time in the reaction cell, it is not necessarily viable yet for treating large volumes of water or treating a constant water supply such as a drinking water well. So these technologies are showing promise for destroying high concentration, low volume solutions of PFAS. So if you have old AFFF or a concentrated leachate from a landfill, these treatment options may be a good option moving forward. So the other emerging technology for PFAS revolves around concentrating PFAS. So basically dewatering and leaving behind the PFAS solution. And so that new technology is called ozofractionation. And so this involves bubbling either gaseous ozone or sometimes just air into a solution of PFAS. And due to that surfactant property in the hydrophilic head group and the hydrophobic tail group, the bubbles that form on the air-water interface are primarily PFAS and to a limited extent water. So you can bubble in ozone or air. You can scrape off the bubbles that form on the surface of your water, and then that is a more concentrated solution than what was going into the influent supply of the ozone fractionation column. And so you can run multiple columns in series and essentially keep concentrating the PFAS in your water and essentially turning it back into an AFFF or a concentrated PFAS solution that could then be either destroyed with one of the above mentioned technologies or clung to activated carbon and then shipped off-site for destruction. So that kind of leads us into the first of our two case studies, which is around the former Pease Air Force Base. So Pease is located in Portsmouth, New Hampshire, on the seacoast. The base was formed in the early 50s, and it shut down as part of the base realignment program in the early 90s. And so since the early 90s, and the land was transferred over to the Pease Development Authority, who still uses the runway that was part of the Air Force Base. It's now split between commercial flights and the New Hampshire Air National Guard. And the land from the base is now used primarily as office space, but there's also manufacturing, college buildings, golf course, restaurants, daycare centers. So a whole host of different activities are going on with the former base land. So in the 80s, late 70s, early 80s, it was discovered that there were VOCs in the groundwater at the base. And one of the larger wells that supply drinking water to the base, called the Haven Well, which is kind of centrally located in the base near the taxiway, had VOCs around it, but not necessarily in the well itself. So in the mid-80s, a water treatment plant was built in the event that the VOC plume migrated towards that well. And in the early 90s, as part of the base realignment program, the EPA designated Pease as a Superfund site to try and cleanup started in that time frame to try to remove all the VOC plumes. So due to the closure of the base and the increase in groundwater quality as a part of the Superfund cleanup activities, the water treatment plant, which had aeration and GAC filters in it, was never activated. It was never triggered. The VOCs never migrated to the Haven Well. So in 2013, that old equipment was demolished from the water treatment plant, and the water was never contaminated with the VOCs, so it just got to go out to the distribution system. A few months later, though, the Air Force tested the wells around the base for PFAS, and it was discovered that there was high levels of PFAS in the Haven Well. So just a few months after they tore out the old GAC filters, it was discovered that there was PFAS in it, and immediately the well was shut down. So once it was discovered, though, that there was PFAS in the Haven Well, it made a lot of local news. The Haven Well was used as a drinking water supply for the Pease area after the base was shut down. And so there was a lot of concern about the health impacts of what the exposure to PFAS, the high levels of PFAS would have done to those that were drinking the water at the time. There was a lot of focus from local and state politicians. So here are some pictures of Senator Jeanne Shaheen and was former governor, now current Senator Maggie Hassan. Both have talked at length and sponsored bills regarding PFAS and cleanup at the former Pease base. And so early on, technical response teams were formed to try to evaluate the situation that was at hand and to try to understand where we were at in terms of science of treatment, health impacts, and what exactly PFAS exposure does. So the technical response teams included the City of Portsmouth staff who operate the drinking water system at Pease, the Pease Development Authority who owns the drinking water system, EPA, New Hampshire Department of Environmental Services, the Air Force, who had taken responsibility for the contamination from the PFAS, New Hampshire Health and Human Services, and the ATSDR to provide feedback from a toxicology standpoint. Several advisory boards and community assistance panels were formed to try to explain the situation to the greater public. And so there's currently a restoration advisory board still underway to try to work on overseeing the remediation efforts of the groundwater supply. And there's also been extensive blood testing in the area to try to figure out if the PFAS that was in the water had made it into the blood serum of those that drank the water. And so blood testing results showed that there was higher PFAS levels than the national average from those that were in the area. And so more blood testing is underway and is being discussed. So here's a nice little graphic of the former Pease base. The red outline was the extent of the base. So really there's 3 treatment systems in this area. There's the Site 8 remediation system. Now Site 8 was the former firefighting training area on the north end of the base, and that is where we see the highest concentrations of PFAS in the groundwater. There's the AIMS, or the Airfield Interim Mitigation System, which is kind of centrally located between the runway and the airfield near the main hangar. And so both of these remediation systems are pump and treat systems relying on GAC and ion exchange resin for treatment. And then finally, the third treatment system is the Grafton Road Drinking Water Treatment Plant, which is that old water treatment plant that was never activated in the 80s. And it will treat water from the 3 public supply wells, the Haven Well, which is again centrally located between the runway and the airfield, and the Harrison and Smith wells, which are on the southern end of the former base. So when we look at the flow rates and the concentrations from the 3 public supply wells, initially the Haven Well, the high producing well in the center of the runway, came back at around 2.5 or 2,500 parts per trillion for PFAS. Subsequent sampling has shown that the concentration has declined slightly, and so we're now around 1,500 parts per trillion of PFAS and PFOA. The Harrison and Smith wells, which are further away from the runway and separated from any major crash sites or AFFF release sites, have significantly lower concentrations of PFAS and PFOA, between really 10 and around 30 or 40 parts per trillion. So looking at the existing building structure, this was the old treatment plant that was built in the mid-80s. There's some old pads in there where the GAC filters used to sit, but largely it's been gutted. The water from the 3 wells comes to this central location. Chemicals are added, the water is disinfected, and then it goes out to the distribution system. So one of the requirements from the Air Force with this project was that this building be reused as part of the new project. So initially, the water from the Harrison and Smith wells was diluted from water pumped from the Portsmouth water system, which is on a different pressure grade. So after a lot of public outcry and an effort to be abundantly cautious, it was decided that we needed to put some sort of temporary treatment on the Harrison and Smith wells so that there was essentially no PFAS getting into the Pease public water supply. So at the time, this was early 2016, we were relying primarily on GAC as the tried and true treatment technology at the time. And so we wanted to just do a quick pilot study to make sure that there was no secondary impacts associated with putting GAC filters on these wells. And primarily we're looking at pH because the city uses an orthophosphate for corrosion control. We wanted to make sure we were within the limits of the pH for that product. So after we did that quick pilot, we decided we needed to install the full-size demonstration filters. And so we ended up installing two 10-foot diameter, 20,000-pound GAC vessels within this old building. And so that did a whole host of different advantages for us. It allowed us to test GAC on the Harrison and Smith wells. It gave us time to look at the market and to figure out if there are any other treatment medias that were out there that would be more advantageous. It allowed us to try to evaluate the regulatory landscape at the time. So at this time, we were right around when EPA changed the health advisory to the 70 parts per trillion for PFAS and PFOA combined. And so there was a lot of question about if that was the final number or if there would be more movement from a regulatory standpoint. And having those temporary filters in place also gave us time to work on the permanent design that would work for treating the Haven well and allowing us to bring the Haven well back online. So here's kind of a quick schematic. We have the water from the two wells, the Harrison Smith well, come together and goes through the two GAC filters, which are operated in lead lag. Because the Haven well accounted for almost 50% of the capacity of the water supply for Pease, we needed to continuously pull supplemental water from the Portsmouth water system, and that was added downstream of the lag filter. Here's a few quick photos of the installation of the GAC filters in the existing treatment plant. There was no knockout wall to install the filters, so I ended up opening up a section of the roof and dropping them in by a crane. And as you can see on the photo on the right-hand side, these filters, which are 10-foot diameter, are roughly 21 feet tall. And so they are quite large, and they have quite a large footprint in this building. So those filters were installed in September of 2016. And since then, it's been almost 3 years. We've treated a little over 400 million gallons of water. And in that time, we've changed out what's equivalent to 3 filter vessels or 60,000 pounds of GAC. In March of 2018, so after around 17 or 18 months of operation, we changed out the media in the second vessel, the lag vessel. And that may be counterintuitive because you would see higher levels of PFAS in your lead vessel. But we did that so that we could prevent short chain compounds from making it through the lag vessel and into the distribution system, and allowed us to have more time to try to evaluate the breakthrough curves of some of these long chain compounds in the lead vessel. We also changed out both the carbon in both vessels in November of 2018, and that timing was based primarily off of a decision to not change out media in the winter, because this is all still a temporary setup, and we use frac tanks and hoses outside and groundwater discharge to get rid of backwash wastewater, so we didn't want to do that in the winter in New Hampshire. And so we really wanted to do it when it was still warm enough out. We also didn't want to do it too late in the event that we'd have to change it out in the winter. So since November, there are some of the results that we've seen for the different compounds moving through the lead and the lag vessels. What we see is that the long chain compounds move through much slower than the short chain compounds. And recently we've switched from a 20 part per trillion reporting limit to a 2 part per trillion reporting limit. So we think we're starting to see things not necessarily move through faster, but we're starting to get more accurate results of how quickly things are moving through the filters. So given that the concentrations are significantly different in the Haven well compared to the Harrison and Smith wells, we decided we need to do additional piloting at the Haven well to see how the GAC would perform. So we partnered with ECT2 to do a side-by-side pilot comparison of ion exchange resin against the Calgon F400 granular activated carbon that we've been using in the demonstration filters. And here are a couple quick photos showing the setup. Each media is placed in 4 columns, and each column corresponds with 2.5 minutes of contact time. So this allows us to kind of sample essentially at the various bed depths through a large filter. So pretty much early on in the pilot study, we realized that we had some pretty significant results. The graph on the left-hand side shows the GAC performance for total PFAS. So at the time we were sampling for 23 compounds. So this would be adding the results from all 23 compounds together. The black line is your influent concentration, and your lines below that, the colored lines, are the sample ports after the various amounts of contact time. So on the left-hand side, we see GAC, which had pretty much immediate movement of some of these compounds compared to the ion exchange media on the right-hand side, which sees much more gradual movement of the PFAS compounds. At the time, we were focusing primarily on PFOS and PFOA, and so these are the graphs for those 2 compounds added together. So essentially removing all the short chain compounds from the list. And we still see very significant results. On the left-hand side, we see GAC, again, very fast breakthrough at the 2.5 minute and at the 5 minute contact times. And that is very significant compared to the graph on the right-hand side with the ion exchange resin, showing pretty much non-detect results for PFOS and PFOA through essentially the entirety of the study. One other interesting thing of note is the performance for short chain compounds. So on the left-hand side, we have a graph for GAC based off of PFBA, which is a 4-chain compound. We see that after essentially a week or 2, we are seeing a sloughing or a release of the PFBA. So our theory is that because it is so weakly absorbed to the GAC, longer chain compounds such as PFOS or PFOA can come through and essentially displace the PFBA, causing this effluent concentration that is significantly higher than our influent concentration. On the right-hand side, we see the performance of ion exchange resin, which may have slight releasing effects, but much less significant than what we saw with the GAC. So based off these pretty significant results, we decided that we needed to kind of reevaluate our treatment strategy. Some conclusions from the pilot was that the resin performed significantly better than the GAC on the high concentrations of PFAS that we have in the Haven well. The resin outperformed GAC with regard to short chain removal. And sort of as the whole regulatory question, as regulations move lower and lower, the advantage of using resin seems to increase compared to GAC. So when we look at the final design for the Grafton Road plant, we are looking at essentially this real crude schematic. PFAS will be removed through a lead lag pair of resin filters. And then due to the concerns of the legacy compounds in the aquifer, we decided we needed to have a GAC filter kind of as a polishing on the effluent of the side of the resin filters. And so because we're stacking all of these filters in line, we have to pay attention to our head loss. And so we have a set of booster pumps that will increase the pressure from the wells. During the design, we did a quick life cycle cost analysis to kind of compare the cost associated with using GAC only versus relying on resin or some various different options. And so while we saw that the equipment cost was highest for installing the resin filters with the GAC and polish, it had the lowest 20-year life cycle cost. So here's a kind of a rendering of how the equipment fits in the existing building. The where the arrow points to the influent manifold and where the resin vessels are shown is the existing building. And because we have so many filters due to the various demand for the water at Pease, we had to install 2 new additions. One addition on the left-hand side is going to house the large GAC filters, and the new addition on the right-hand side is going to be a control room laboratory space. And here's a rendering. Again, the central portion of the building is the existing structure, with the new addition shown off on the sides. So that kind of gets us to our second case study, which is the work that we are working on right now at the former Fort Devens, located in Devens, Massachusetts. Former Army base that shut down in the mid-90s, and is majority is overseen currently by Massachusetts Development, which is a state-run agency who's tasked with developing the economy in this area. And so much like Pease, it's a space with a lot of offices and warehouses. There's, again, a college and a golf course and restaurants in this area. So again, we are seeing water system demands that are not overly consistent. We see high demand during working hours, during a normal kind of 9 to 5 times, and much lower demands on the weekends and in the evenings. So similar to Pease, Devens has 3 wells. These are larger wells from a flow standpoint than is at Pease. The McPherson Well on the north side of the former base operates at 650 gallons a minute, and its concentration is the highest at around 120 parts per trillion. And then on the southern end of Devens is the Patton Well and the Sheboken Well. Both of those are rated for 1,200 gallons a minute, and both of those have around 30 parts per trillion for PFAS. So in Massachusetts, though, we are looking at 6 compounds added together. That's PFAS and PFOA, plus PFH-XS, PFH-PA, PFNA, and PFDA. So all of these compounds are added together when we look at the concentrations in these wells. Massachusetts has been moving quite fast recently from a regulatory standpoint. Again, in May 2016, the EPA dropped their health advisory for PFAS and PFOA to 70 parts per trillion for the 2 compounds added together. In June of last year, Massachusetts Office of Research and Standards released an ORSG for essentially 5 compounds added together needed to be less than 70 parts per trillion. So at that time, Devens had turned off the McPherson Well, which, to remind you, had around 120 parts per trillion in it, and we're relying on the Patton and Sheboken Well, which had around 30 parts in it. Due to the size of the wells and the current system demands, they could rely on just having the 2 wells, and they could essentially mothball the McPherson Well if that was what they had chosen to do. However, in April of this year, Massachusetts revised their standard and released a new, what's called a GW1 or groundwater 1 standard, and that level is 20 parts per trillion for 6 compounds added together. So it's the previous 5 plus PFDA. So when this new level was released, it significantly impacted Devens in that they had no wells that were in compliance with this 20 part per trillion level. And so that moved them from thinking about what to do with the McPherson Well to now they have to figure out what to do with all of their wells. At this time, they were handing out bottled water to whoever wanted it, and they had a advisory posted around the Devens area and on their website. So initially we looked at the McPherson Well. Early design concepts were being routed out once it was shut down for the 70 parts per trillion limit. And just to remind you, it's a 650 gallon a minute well, around 120 parts per trillion for PFAS. And so one of the issues for the McPherson Well is its land constraint. Here's an aerial showing the buildings and the structures in this area, and then kind of a fence line that goes around the perimeter of their land. And they do not own much land outside of that fence. And so to try to find a place where we can install a permanent building, we really only had one location on their land, kind of in the bottom left-hand corner there. And so that really left only essentially one option to put in a temporary filter to try to remove PFAS from the water as quickly as possible and to lift their drinking water advisory. And so in the top left right-hand corner is the location where we decided to drop a single 10-foot GAC filter on the site. The filter is rated for 400 gallons a minute when that is at our industry standard 10-minute empty bed contact time. And so based off of the urgent nature of installing these filters, it was decided that we would install the filter, install the media, get it conditioned and online as quickly as possible. We would worry about building a structure to heat the filter at a separate time. So here's kind of a setup, a picture showing the filter and how it was installed in that tight space. The filter was placed by a crane that brought it over the chem feed building. The raw water main that's in the ground, kind of between the pump station and the chem feed building, was teed off. The water was routed to the influent side of the GAC filter, and then the effluent was routed back into that line. So the plan is to install an insulated stick-built structure around this filter in the coming months, and install a temporary heater so that we can use this filter in the coming winter. So really from the time where we had our first sit-down meeting with the state environmental agencies to the time where we started up the filter was around 4 months. So a pretty fast response time to get a full-size filter on place to treat the water. So with this filter online, attention was shifted to the Schematic well. The well is rated for 1,200 gallons a minute, and again has PFAS around 30 to 40 parts per trillion. So the advantage at the Schematic well is that we do not have land constraints. And so we have a nice large open field next to the Schematic well where we could drop in 2 pairs, so 4 total vessels that are 12-foot in diameter and hold 20,000 pounds of GAC each. So going off our 10-minute empty bed contact time, we can operate these filters at around 900 gallons a minute in a lead-lie configuration. And between the flow from these filters and the flow at the McPherson well, we could at least satisfy system demand and try to lift the drinking water advisory. So here's a photo of where these filters currently stand. We did a little bit of leveling of the ground in that area, brought in some crushed stone, installed a pair of concrete pads for the filters, and then have been working on bolting up the filters. And then currently we're still working on conditioning the media, but we expect it to be stabilized in terms of pH in the next week or two, and then these filters will be sent to the distribution system as well. Looking at Devens' third well, the Patent well, again, it's the same size and same concentration of PFAS as the Schematic well, but we have the same issue that it is very much land restricted, similar to the McPherson well. So given that the other 2 wells, the McPherson and Schematic well, are large enough to satisfy system demand, we thought we could try out ion exchange resins at this site. And that is also advantageous in that they don't take up as much footprint as the larger GAC filters. So our current design is to use 3 4-foot diameter resin filters in parallel. Each resin filter is rated for 200 gallons a minute, and the flow will go through in parallel. So this setup will allow us to test 3 different resin filters and essentially have a full-size pilot setup where we can test different media to try to optimize for a more permanent system. So these filters, being small enough, can be installed in an insulated storage container or a shipping unit. So that'll be dropped on site. The filters will be bolted up, and we should have this system online by around December of this year. So as Steve referenced last week, a few useful websites. Moving forward, should you have any questions on PFAS, the ITRC website is fantastic. They update it multiple times per year, and they stay on top of state regulations and treatment technologies and analytical processes that are rapidly evolving in the PFAS world. The EPA, of course, is a useful reference for PFAS. And then Northeastern University is working on compiling a lot of useful PFAS information from around the country. So I think at this time, if anyone has any questions, I'd be happy to answer them.
Great. Yes, we've been getting tons of questions, so we should jump right into those. The first thing that I'm going to do, though, is just send a quick link in our chat to our evaluation form. So you should all receive that. If you would like to fill out the evaluation for this webinar, you can. You'll also receive it in an email from us after the webinar. So I am sending that now so we can get right into the questions. So the first question has to do with using granular activated carbon, or GAC, after it's been used to treat the water and you're removing it off-site. How does the incineration serve to destroy the PFAS?
Sure. So in a reactivation facility, it's essentially an incinerator. So once the carbon arrives on site, it is deposited in essentially what's called a hopper, and it is heated up to over 1200 degrees Celsius. And so in this reactivation process, in this incinerator, the temperature is hot enough to destroy all organics that are on the PFAS or on the GAC, but also the PFAS. So that temperature is high enough to break down that carbon-fluorine bond that holds the PFAS together. So it essentially off-gases in that facility. And so the temperature, though, is high enough that the GAC, which is essentially elemental carbon, does not burn up, so it remains behind. So this process allows the spent GAC essentially to be reactivated, to be cleaned up. All the contaminants that are on it are burnt off, and the clean GAC is left behind.
Fantastic. Thank you. So the second question is about if you have any guidance for how to go about determining if firefighting foam was used at a site, and maybe what the first steps are in determining that.
It's a good question. And that is definitely somewhat site specific. So there's certain key things you're going to be looking for in trying to evaluate if you're trying to figure out if you want to even sample or not. And that would be, are you near an active airport, or have you been near any sort of airline related crash? Because oftentimes those crashes, the fires associated with them, are put out with firefighting foam. Fire training areas, even if that's just a small local fire department, oftentimes will practice with AFFF in the event that they have some sort of hot burning fire that they need to put out. They will oftentimes just have a small amounts of AFFF around. So there's no real tried or true relationship with has AFFF been used. It's definitely not used for all fires, and I wouldn't even say it's used for the majority of fires. But if you think there's a chance that there was a hydrocarbon or like a kerosene or jet fuel fire, that there's a good chance that AFFF was used. The only way to really confirm would be to try to grab a groundwater sample in that area.
Awesome. Thanks so much for that. I think that answers that question very comprehensively. So switching gears a little bit, you mentioned in your example about the Pease Air Base that the GAC worked well with lower concentrations of PFAS. So can you just describe how you learned that one more time, and then also what the threshold for those concentrations were, or how you were defining or looking at lower versus higher levels?
Sure. So at the time, sort of early 2016, GAC was really the only option that we were looking at. We knew RO systems would work, but that does not really lend itself well to a temporary system. So GAC was really the only option that we had. When we decided that it was kind of a worthwhile solution for low concentrations, that was primarily based off of the results we saw in the kind of initial installation of GAC media in those filters. So we ran the lag vessel for 18 months and we ran the lead vessel for 24 months. In that time frame, we saw the compounds move through, but we didn't see significant movement of the long chain compounds of concern, PFAS and PFOA. And trying to essentially decide with the city of Portsmouth and their operators what was an acceptable amount of GAC to exchange at any given time. We decided that one GAC change out per year or every 2 years seemed perfectly sufficient in their mind in terms of O&M for a filter. So where is that threshold of between low concentration and high concentration? It's hard to say. GAC works well for a lot of different water quality characteristics. Ion exchange resin can be a little more finicky if you have high levels of TDS or chlorides or sulfates in your water. Ion exchange might prove to be a little less useful, but probably somewhere in the 100-200 parts per trillion range is where you're going to see a pretty significant lean towards the ion exchange resin if it works for your water quality.
Okay, great. And so we are hitting the top of the hour, so it's a little bit past 2. I think we can stay on the line a little bit longer for some questions, but for those of you that do need to leave, we understand. So just to keep going with some of these questions, the next one is, what treatment solutions exist for treating surface waters, like lakes and rivers, and are they different than the ones we discussed?
Surface water can be definitely trickier than groundwater. The treatment technologies for PFAS and surface water do not differ from what we see for groundwater, so you're still limited to GAC, resin, or membranes. However, you might have to have additional filters or additional steps to try to remove other contaminants that may impact your filter performance for PFAS. So that may be TOC. Maybe you want to have an extra GAC filter that's more as a roughing filter to try to remove or reduce your TOC concentrations before you have a primary PFAS removal filter. You might have to have additional bag filters or cartridge filters to try to remove suspended solids or turbidity that may not be required with a groundwater treatment system.
Great, and we are getting a lot of questions about the human health impacts of PFAS, and specifically about whether there's reason to believe that drinking water is a larger contributor in terms of health impacts than other PFAS sources. I don't know if you could speak just a little bit generally about PFAS health impacts. And also, before you start, I will say we did cover this a little bit in our previous webinar. So if you need a little bit more information on this, feel free to go there after this webinar as well. But I'll let you, Kyle, maybe describe a little bit about this topic.
Yeah, it's definitely a debated topic, and I will say I am no expert on this. I'm not a toxicologist. I'm an engineer. So what I do know, though, is that it is debated. We've seen reference levels anywhere from 20% to 80%. So that would mean anywhere. So that would mean essentially anywhere from 20% of your PFAS exposure comes from drinking water to anywhere to 80%. So it's much debated right now in the toxicology world of how much PFAS an average American's exposed to if it's not in their drinking water. But that's the best I can do on that one.
Thanks. No, I think that really does well to cover it. And again, on efcnetwork.org, the first webinar on this topic aired last week, so you can find it under past events, and you can see that recording. Steve LaRosa colleague of Kyle's, did a wonderful job talking about this. And I think we have time for just one more question. I know there were a ton of questions this time, so if we didn't get to this question, we'll do our best to get back to you in some way, shape, or form. But for our last question, can you just talk about this one last issue? What about the pH impacts of granular activated carbon? You did mention this really briefly, but if you could expand on that quickly, that'll be our last question for today.
Sure. So we did the first pilot study because we were concerned about pH. We had heard that when you install GAC, virgin GAC on a water supply, oftentimes it drives the pH way up for a certain amount of time before it starts to level off again. And so trying to stay within the city's corrosion control requirements, we had a certain pH we needed to stay under. The pilot showed that we did see high levels of pH, and so during the demonstration study, the initial GAC that we installed had an acid coating on it. That acid coating is supposed to help neutralize the pH on startup. And for our water supply, we actually saw it do a little more harm than good. We saw the pH drive significantly down on the acidic side. As that acid coating started to wear off, the pH shot back up to what it was with standard virgin GAC. So from our experience in talking with the GAC vendors, acid-coated GAC or acid-wash GAC is useful for about, they said around 50% of customers that try it out. Some it works great in stabilizing your pH, and some it does not seem to do that.
Wow. Thanks so much, Kyle. This was fantastic. I know we do have a couple more questions. We'll try to get back to you via email, but at this point, I'd like to hand it back over to you, Kyle, for any closing comments, and we can wrap up for the day.
I just want to say thank you, everyone, for listening. PFAS is a fun, interesting topic, and it's definitely evolving, and we're all trying to do our best to stay ahead of it and see what we can do moving forward and developing new technologies that will help us make this a more viable treatment going forward. So thank you, everyone.
Thank you so much, Kyle. Have a great day, everyone.